Uh, our next speaker is Paul, and he hails all the way from, we're moving from Tennessee to New York, and he works in a pretty interesting space, which has everything to do with mirrors. I'm joking. But as you can notice from the talk that he's going to be giving, it's all about reflection. And the interesting part is we reflect back on his past. He is actually not from New York. He told me that, you know what, I was brought up in this place called Islamabad. So he actually hails from our neighboring country, Pakistan. And he spent a lot of his childhood there. He plays the classical music. He plays the piano and the violin. And is currently working at Deaf Method. And he's going to speak about reflection in Ruby. And has built this awesome gem called Dependable, which if you all are not aware of, you will get to know the insights of how it works. So while we are setting this up and Paul is getting ready, I still see that we don't have any more backbenchers, but we have a lot of people standing behind. Should we, all the people who have been kind enough to be seated, give them a loud round of applause for them to walk ahead as chief guests, please, and gather first 2 rows here. Look at all of them walk out. There they're coming. Come, you have places here ahead. Nobody wants to take. Dude, this is not like a stand-up comedy where we're going to take your case on the front row. I'm not sure yet. All right. So, Paul is all getting set up, and we are all getting seated. I did not mention earlier that you need to keep your phone on silent. Do I need to mention that? Do I need to mention whether I have to keep our phones on silent? I guess if you reflect on it long enough, you'll realize it's already been answered. Prathamesh? Where is Prathamesh? So there are a few people, right? The guy there behind, Prathamesh? Raise your hand, Prathamesh. All right, if you all have any kind of problems, issues, suggestions, please feel free to talk to me or Prathamesh about anything during this conference. All right, so without further ado, Paul, the stage is all yours.
Thank you. Hello, my name is Paul, and I've been thinking about the evolution of Ruby systems for a while now. In my work, I've been building systems that automate tasks like updating gems, running the tests, and finding details about those updates. For example, running bundle updates, capturing the CLI output, turning it into a data structure, scanning the RubyGems API to identify the source location, looking up tags on GitHub, and generating a diff for those changes. And what I found is those source code changes, while they're useful, they still require quite a bit of manual reading, and they're not always particularly descriptive of the changes in the system, which led me to an exploration of ways to use Ruby to introspect on the structure and behavior of code over time. So today, I'm excited to share 3 of those techniques with you. We're first going to look at how to detect available classes and methods that change when we load a new gem. And for this, we're going to be using the tools in object constants. So object constants will give us a list of symbols representing the named concepts available in the global namespace. We also have access to the methods available on all objects with object methods. Now we're going to start by building a map of the world with all the constants at the beginning. Then we're going to also grab the original methods. And let's load a gem. So we're going to load the JSON Web Token gem. Then we're going to build this map again. Now, let's find what was added. We're going to find the difference between the updated and the original. And do the same for the methods. So let's go through and print out what was added. for both the top-level concepts and the methods. So we can see here that after loading this JSON Web Token gem, we have a few different classes: OpenSSL, Base64, JSON Web Token. We also have some JSON behavior. Turns out that some of these are from the Ruby standard library. They're not loaded by default. So let's load the standard library items before requiring the gem so that we get a picture of what was unique to that gem. So we're going to require open struct, JSON, Base64, and OpenSSL. So now we can see that we don't have any methods on the global namespace, but we do have this added constant. So if we go through each of these added constants, let's find some additional details within those. So if we printed out the details for that constant, so we first have to get that constant, and then print out the items in that namespace. And then also print out the methods. So here we're going to just show the methods that are different from the original set. So we're going to look at the diff constants. Let's look at the constants and the methods. So you can see here there were some new classes in JSON Web Token for different kinds of errors and signatures. We also have methods for encoding and decoding, which would be expected for a token library. So this technique allows us to identify all of the new named concepts and the methods that exist on those items for any gem that we load, and may provide useful information for digging into the capabilities presented in those external libraries. Next, we'll look at identifying the behavior that has been changed. So Ruby allows us to change the definition of an existing concept through monkey patching. And it's a powerful technique, not one to be used lightly. Sometimes it's not clear whether something has been changed, or perhaps an application might have multiple libraries that make the same monkey patches. So how might one determine whether something has been monkey patched? We can do a similar thing by building a map of the world before and after that change. So we're going to use an example of changing the definition of string equality. So we're going to start off with some examples. Let's see. We're just going to print out some string comparisons. And then, so we have the truthy case, and we'll now do the falsy case. So let's verify that we get true and false as the base case. So now we're going to load something that changes this behavior. We're going to make a new library that is going to change the definition of these methods so that they will reverse. We're going to reopen the definition of string and overwrite equality. Now, in this case, it would be nice to invert the definition of the original equality method, passing in the same input parameter. So to do that, we'll have to alias the original equality method with a new name that allows us to call the unchanged behavior from the new method. Let's take a look at that. So now we can see we've changed from true and false to false and true. Now, if we wanted to ascertain this change without having made it explicitly, we'll once again start by building a map of the concepts in the system. And we're going to build toward being able to make the comparison of the old string equality to the new string equality. So in order to do this, we'll have to have a structure to capture these details. We're going to go through each of the original constants, grab the class representation of it, and if the named concept allows methods to exist, we're going to use instance methods in this case. If it has instance methods, we want to go through each of the instance methods and grab the implementation. So we're going to build the second level of this structure. So at the top level, we'll have a hash for the named concept, and then within that, a hash containing the methods and their signatures, or their implementations. So we have these implementations. We're going to go through each of these instance methods. I'm going to close this library so we have more space. We're going to go through each of these instance methods, and then save the implementation by calling the instance method. This is really the name, so I'll just clarify that. Now we have the implementation, so we can save it. So we've grabbed the implementation, we've stored it in the structure, and after we go through all of the implementations, we can save that collection on the top-level object for this constant. So now we've built the initial set of all methods and their implementations. Now we're going to build a new map after requiring this library. So we're switching from the original set to an updated one. And also this old information is the new set. So having built this representation, we can now go through each of the methods and identify ones that have changed. So this comparison is going to be, once again, old string to new string for the particular instance method. So at the top level, we have the class name, and we have the methods. Now we can go through each of the methods with the method name and the old implementation. The new implementation comes from the new structure for the same class name and the same method name. And if they're different in any way, we want to display that. So we're printing out the class name and the method name for all the methods that changed. So we have yes, thank you. There's always something interesting with a live session. So here, this should not be the assignment, this should be the comparison. So we have this method changed, string equality, and we invoked that method. This will work even if we didn't use the method. For example, if we changed uppercase to a new version and also downcase. We'd also see those methods detected as having changed. This will work for any instance method on any class that existed before and after the new library was loaded. Next, we'll look at how to identify potential changes that may not be actualized in the system. For this one, we'll use an example of comparison of hashes. So we'll build some initial hashes. So we have 2 dictionaries, and let's add a third one. Now, we can print out the comparison of these. This is the control case, which should always be true. We have the comparison of the first 2. And then finally, the third comparison. So we should have false and false. So true, false, and false for these 3 examples. And indeed, that's what we have. True for the hash that is compared to itself, false for the one that's compared with a different value, and false for the one that has different keys. Now, let's change this so that maybe we decide that we want to compare dictionaries or hashes that are close enough. So let's make this new library to allow that comparison. So we're going to have this new library. And this is going to make a module available. And this one will also define equality. And in this case, we're going to decide that the keys will need to equal the keys of the other object. So we've not made use of this module yet, this module. And we're going to reopen hash and prepend the module so that the implementation of equality from the module takes precedence over the definition of equality present in the existing class. So with this change now, we should see true and true, because the keys are the same, one of them differs, and false should still be on this final case. So we have true, true, and false, where we had true, false, and false before. So let's identify that potential change. If we ran the previous comparison to identify the definition or the change in the implementation, we would uncover that, yes, this method changed. But this change came from a module. So we can also see that the ancestry of the class changed over time. For this, we're going to have a comparison of the old ancestry for hash to the new ancestry information for hash. Once again, we'll have the original constants. And then for each of those constants, we're going to capture the class representation. And then if the class has ancestors, we're going to capture the list of ancestors. Having done this for the initial set, gone through all the classes that all the named concepts that have ancestry information and captured the ancestry list. We can now go through and do it again after making this change. So now that we have the updated information, we can go through each of the old classes. Having the list of old ancestors, we can grab the new ancestors. And if they differ in any way, we can print the list of changes that, or the list of new ancestors. So we're printing out that new ancestors exist for this class after having required the library that made the change. So now we can see that hash added an ancestor close enough. If we wanted to apply the other techniques, we could inspect the details of this new module to identify what methods exist. An interesting comparison would also be to go through building a map of all of the modules in the system and then finding the ones that are not currently being used, the ones that never appear as ancestors of other classes. That would provide information such as perhaps you're using a library that exposes a great deal of behavior that is not currently needed, which may, in an ideal world, perhaps allow you to remove that dependency. An example combining these techniques is finding the differences in versions of a gem over time. So here with Rails 5.05 to 5.10, I wrote a script that performed these comparisons, finding the constants removed, finding the constants that were added. There were changes in system tests in Rails 5.1, so it's not too surprising that there would be some changes relating to system test case. There were a number of removals in 5.1. And if we look at the added methods, many of them have to do with integration tests, which is to be expected. One application of this that I think could be interesting is if you know the changes in the namespace to a gem over time, you could, for example, have a script that checks to confirm whether semantic versioning contracts are being held for a new release of a gem. Or rather, you can't guarantee that they're being held using strictly dynamic analysis in this way. But you can guarantee that if there is a violation, say a violation that removes a public method from the API, this technique would allow you to detect that. Building a map of the methods available, it would also be possible, for example, to dynamically generate a monkey patch for that method to capture details like whether it's being used, being able to capture the arguments passed in and the outputs of that method, to be able to identify potential breakages across versions of a library for the same method calls. We've seen this example use case and the potential for finding monkey patches across the system. If you have multiple gems that have the same monkey patches, that might be something to investigate further. For further exploration, I highly recommend the well-grounded Rubyist, which has some sections dealing with techniques for reflection generally in Ruby, and also fundamentals for understanding how method dispatch works and various aspects of the Ruby runtime that are helpful for doing this kind of analysis. Metaprogramming Ruby goes into much more detail on the various techniques of metaprogramming available in Ruby. And these talks present examples of, in Jim Barrick's case, building a lambda calculus with reflection in Ruby. Ryan Davis's talk demonstrates building a version of Minitest from scratch. And Sam Phippen demonstrates aspects of RSpec using Ruby metaprogramming as well. With this exploration, I've been learning about different ways to introspect about a system using the capabilities of the language. I highly recommend thinking about the evolution of a system in this way, thinking about the world of named concepts and behaviors attached to those concepts as both of those change over time. I will say that many of these concepts have applications that probably should not be in your applications directly, but they're useful techniques for troubleshooting, for debugging. If you happen to be in a console on a server trying to identify what behaviors exist in a library, and if the documentation is perhaps lacking, this can help you along that path of finding what behavior might be available to you or what changes might have occurred to render behaviors less accessible than they were before. There's a great deal of potential for applying these concepts. I'm trying to work on tools to automate some of this analysis for developers on their own projects. I'm curious to see what other techniques might emerge in the coming months as there are multiple developer tools working on these kinds of problems. That's all I have for you today. Thank you.
Thank you so much, Paul. That was fantastic. It's not often that we get to see a presentation which is not in Keynote, a taunt to all the other speakers, and so much of live coding. That is phenomenal. I'm sure a lot of you all have actually gone through that code. It was good. I was actually looking behind and seeing a lot of us were actually involved with that code. Did you all like the topic? Did you all like the session? Yes. Did you all enjoy the live coding? Yes. Now, a silent question. Don't answer it, but ask yourself inwards. How many of you all were impressed with the speed of touch typing here? Paul, well done. Thank you so much.